So, good evening everybody. The ABC of galaxy evolution. There's only three things you need to know about how galaxies form and how they grow, and by the end of this evening, after the next 2 or 3 hours, whatever it turns out to be, you will understand what those ABC factors are. When we look out into space, either with the Hubble Space Telescope or perhaps with ground-based telescopes, we see these wonderful structures. We see these beautiful spiral galaxies. Sometimes we see galaxies that appear to be distorted. Perhaps they're interacting with other galaxies. Some of them are grand design, like M101, this beautiful face-on spiral, and some have rather different structures. For instance, this huge bar in this barred spiral. And some are perhaps less aesthetically pleasing, elliptical galaxies that apparently have no real structure. But at the end of the day, we want to understand how these galaxies come to be and how they end up looking the way they do. The three factors, I'm going to say them up front rather than leave you hanging. The ABC, the three factors are A, for accretion. In other words, galaxies form by matter created in the Big Bang, accreting, agglomerating if you prefer, under the influence of gravity. So that's the A. The B stands for black holes. Supermassive black holes at the centres of many galaxies, possibly even all galaxies bar a few. Black holes are very common at the centres of galaxies. Some are feeding on the surrounding matter which is falling into the black hole and hence are very active, and some of those black holes are quiescent, no longer feeding on any surrounding matter. And finally, the C of the ABC is collisions. In other words, galaxies grow by colliding and merging with other galaxies over a course of perhaps many billions of years. So there's the ABC, which we're going to approach after I've given just a little bit of introduction. So where should the story start? Well, every story starts at the beginning. In this case, the beginning of everything. And as Sue mentioned, 1 year ago, almost to the day, there we see the date, BASoc, 17th of February 2020. That's when I gave you a talk about how the universe began. Do you remember that a year ago? Do you remember what life was like a year ago when we met in person in the rugby club? Well, those were the days, eh? But yes, 1 year ago, I told you about how the universe began, how in 3 minutes the universe was created and made all the hydrogen that we see around us, which ultimately gets converted into all of the other elements. In the beginning of everything, I told you that everything we currently see in the observable universe, everything that's currently within tens of billions of light years of us, everything used to be in a volume approximately the size of a golf ball. And not only was it approximately the size of a golf ball, the universe had dimples, just like a golf ball. The dimples in this case were variations, very small variations in density and temperature, which ultimately gives rise to the structures that we're talking about this evening. The universe expanded from the size of a golf ball for 100,000 years until it eventually produced the cosmic microwave background. In other words, when we look at the cosmic microwave background, this is an all-sky map, we see variations in the intensity of microwaves, and these are, in a sense, a ghost image of those dimples in the golf ball. So we have variations in density or variations in temperature that we see across the sky in the early universe, but the question is, how did we go from there, a fraction of a million years after the Big Bang, to where we see the universe now, a structure essentially full of galaxies? If we look in the Hubble Deep Field, we're looking at close-by galaxies and very remote galaxies, and we see galaxies essentially everywhere. Some look a little bit blue, some look a little bit red. We see galaxies that have spiral structures, we see galaxies that have very little structure, they just appear to be elliptical blobs. But what we want to try and get to grips with is how did the universe go from a golf ball to something that produced the cosmic microwave background? How did we get from there to this sort of picture, a universe full of galaxies? Well, the answer essentially is we can only understand how that came to be through simulations. Yes, we understand what the laws of physics are on the whole, but still, to work out how we go from something so small to something so huge and how we get all of this diversity of structures that we see around us, we have to rely on simulations. We have to rely on a computer that basically is filled with everything we know. Let's fill the computer with a whole load of hydrogen and other matter. Let gravity do its stuff and then see what happens according to the laws of physics. This little snapshot you can see on the left-hand side are lots of different simulations which have been carried out over the past few decades. And I'm going to pick on just one of those simulations because I certainly haven't got time to talk about all of the detail of all of these. I'm going to pick on one group of simulations that's been carried out in the last few years. It's the so-called Illustris suite of simulations. And we're going to look at how these computer simulations help us understand how we've gone from the early universe to the structures of galaxies that we see now. So I've already mentioned that the dimples in the cosmic golf ball, when the universe was only a few centimetres or so in size, in other words, what we currently define as the observable universe, all of the matter in that volume was an awful lot closer in the early universe. And the dimples in the golf ball gave rise to the cosmic microwave background variations. And then, over billions of years, we see that particular structure collapse under gravity. And the dimples give rise to variations, and it's those variations that give us the interesting bits of the universe, i.e. ultimately galaxies. So let's have a look at the first simulation of how a relatively uniform structure, such as the golf ball with a few dimples in it, let gravity do its stuff, what happens over the next few billion years. So this is a simulation of a certain chunk of the universe, not the entire universe, but a spatial scale of many millions of light years. It's almost the same everywhere, but there's just slight variations in density in this particular structure. And now we're going to let the simulation run and ask gravity to do its stuff. What happens? This is what happens. The structure collapses into a sort of web of filaments, and in between the filaments, voids. And we can see where filaments intersect, we get little hotspots. This is where the galaxies are forming. In the top left, you can see a white blob, so a particular cluster of galaxies forming here. You can see these tendrils, these filaments. Some areas appear to be relatively devoid of matter, and other areas appear to be quite concentrated. This is what gravity does. It takes small variations in density, and over time it turns them into large variations. Matter is starting to clump together. If you watch what's happening here, for instance, in this top left-hand corner, whilst I rerun the video, let's just run it again, you see these filaments are forming, and perhaps you can see that matter is flowing along these filaments and starting to gather and agglomerate or accrete in these regions, these little knots where the filaments cross each other. So that is the first step of the formation of galaxies, is the creation of this cosmic scale web of filaments of matter, and matter is draining down those filaments and concentrating into these little knots where the galaxies ultimately will form. The densest parts of the filaments, that's where we identify the nucleation points. The density is high enough to start to form galaxies, clusters of galaxies, and ultimately superclusters of galaxies, depending on how much mass there is in a given volume. And matter essentially flows through these filaments. The filaments start to form under the collapse due to gravity, and then matter tends to flow through these filaments, and so a galaxy is effectively accreting mass from these filaments. Along the way, we have to take a few other things into account. It's not quite so simple as start with a lot of hydrogen and then let gravity do its stuff and see how that all collapses. If we want these simulations to actually tell us something about the real universe, if we want them to be realistic, if we want to learn something about how the simulations produce these galaxies, we must take into account that at the same time the galaxies are forming, so are the stars. I'm not going to talk a lot about the detail of star formation or star evolution, but star formation must be built into these simulations because as stars start to form, they live, they die. Some stars produce supernova explosions, which sends matter hurtling out from the stars. Some stars form black holes, and the matter falling into black holes can again produce outflows. So although most of the mass is trying under gravity to collapse into a galaxy, at the same time some of the stars that are evolving are impeding that inflow. And if you don't put that into your calculations, you don't get realistic galaxies. So it's not quite as simple as start with hydrogen, switch on gravity, let it do its stuff. You must build in a certain amount of additional physics, the physics of how stars ignite, the physics of how stars live, the physics of how stars die. That must be built into the simulations. So I'm not going to talk in detail about how the simulations work because ultimately they are very complex calculations and they must take into account a lot of different factors. But that notwithstanding, we can still get a good idea of what's actually going on. The bottom line is, if we run these simulations, can we explain, for instance, the diversity of galaxies? When we look at what's out there with either not necessarily a Hubble Deep Field, but just a snapshot from any ground-based telescope, we see lots of different structures of galaxies. They're catalogued here, for instance, on the left-hand side, we have a number of bluish galaxies. These tend to be disk-like galaxies. They tend to be quite thin. They are usually circular when they're seen face on, but they can be quite thin when seen side on, so they're disk-type galaxies, quite often with spiral arms. They tend to be bluish, and they're on the left-hand side of this particular picture. And there are a whole host of galaxies which don't seem to have any internal structure. They don't seem to have spiral arms. They appear to be just elliptical blobs, and they appear a little bit redder, and they're over on the right-hand side of this diagram. But if we run a simulation, we hope to be able to show that any of these galaxies could come into existence. If we run a simulation and we don't see the sort of galaxies that we observe in the sky, then our simulation is failing to capture some essential physics of what's happening as the early universe evolves into the universe we see today. So let's think about the ABC. First, let's think about how matter accretes to form galaxies. Before we actually look at a video of the accretion process, let's just say a few words about the simulation itself, the illustrious simulation, one of many that are in existence. The Illustrious project is a set of simulations that tries to map out the evolution of everything, essentially, from just after the Big Bang to the present day. That's quite a feat. And along the way, it has to take a lot of things into account. It has to take into account the fact that the universe is not just full of hydrogen. We know the Big Bang produced a lot of hydrogen. Presumably, it also produced a lot of dark matter. We know dark matter is out there, so it has to be in the mix as well. And there has to be an awful lot of it. I've already said that along the way we have to take into account the fact that as matter starts to accrete, stars start to live, stars die, supernova and black holes can produce outflows of matter as well as gravity producing an inflow of matter. So if we want to see matter accreting into galaxies, all of this has to be taken into account. And the simulations are not simple because of all the physics that has to be built in. That's why we couldn't really do these calculations 20 years ago, because computing power wasn't up to the job of taking a large volume of space and building all of that physics into the simulation. But now, with the advent of supercomputers that are capable of doing number crunching with an enormous number of calculations per second, now it is feasible. The illustrious simulations ran for approximately 20 million CPU hours. CPU is central processing unit. So treat that as 20 million computer hours if you wish. And those simulations ran not continuously necessarily, but they ran over the period from about 2013 to 2015. When those simulations were running, the people who designed those simulations realized that they could make them a little bit better. So they were followed by an even more sophisticated set of simulations. What did they decide to call those? Did they call them Illustris version 2? No, they didn't. They had more of a sense of humour, and they called them Illustris the Next Generation. Fantastic, what a great name. So from here on, I will use the abbreviation TNG to refer to this latest set of simulations. The TNG simulations ran for 10 times longer, 200 million CPU hours, approximately between 2017 and 2019, and then the results were published fairly recently. They were running on a Cray supercomputer, and just to give you an idea of the relative speed of these things, if you ran these simulations on your desktop computer, you could expect one of the simulations to take maybe 20,000 years to run, assuming that there were no updates during that time that interfered with the run of the simulation. The TNG simulations were carried out on a number of different spatial scales. There they are, 50, 100 and 300 million parsecs. We'll come back to parsecs in just a moment. In other words, they were carried out on a very large scale, a cube of space, 300 million parsecs on a side, was taken to give the overall structure of what the cosmic web looks like. But on a much smaller scale, in the bottom left there, TNG 50 were carried out on a smaller cube of size 50 megaparsecs in order to give us the detail of what's going on within one or a small number of galaxies. And an intermediate scale simulation was done to make sure everything ties together. Let's just remind ourselves that 50, 100 and 300, those are the numbers used in the simulation, but those are equivalent to 150, 300 and 1000 million light years. A light year is about 3 megaparsecs. Let's just pause and remind ourselves about light years and parsecs. 1 parsec is a little more than 3 light years, and amateur astronomers, quite naturally, prefer to use light years. It's a sort of fairly reasonable measure of distance. How far does light travel in a year? So we know stars are typically light years or many light years apart, and the distance from us to galaxies is millions of light years. But astrophysicists, bless them, they prefer to use parsecs rather than light years. So let's just remind ourselves, let's just think of the Milky Way as a yardstick, if you like. The diameter of the Milky Way is maybe 150,000 light years. So that's about 50,000 or 50 kiloparsecs. And I think the best yardstick to keep in your head, if you don't like parsecs rather than light years, the best yardstick is to think of how far is it from the Milky Way to the Andromeda galaxy. That distance is about 2.5 million light years, so that's just a shade under 1 million parsecs, or 1 megaparsec. So when we talk about megaparsecs on the following slides, just remember that a megaparsec is, roughly speaking, the distance between fairly close galaxies, such as the Milky Way to the Andromeda galaxy. That's the only real yardstick that you need to keep in your head. So let's have a look at the accretion process. This is a scale, as you can see on the left, we're talking about kiloparsecs, so we're talking about a scale which is roughly the size of a galaxy, such as the Milky Way. And what we're going to do is to run the TNG simulation over a few billion years. And this particular point we're looking at is one of the knots, one of the junctions, if you like, between these filaments that we saw when we looked at the cosmic web. So matter is flowing in through the filaments and accumulating roughly at the centre of the screen. So what we're seeing is a galaxy effectively being born. Matter is flowing in from these filaments and accreting into the middle under the influence of gravity. You can see it's fairly chaotic to start with, and every once in a while we see a little clump floating around. Maybe that's a little galaxy trying to form, and you can see that one galaxy is effectively cannibalizing other galaxies as the matter streams are flowing in to the middle of this particular image. There's another little knot that appears to be coming in, and I guess by gravity, yep, there it goes, it's being captured by this object we see. There's another one coming in. So after a few billion years, you notice that most of the matter, which is coloured yellowish in this particular simulation, has fallen in from these filaments. Notice that the surrounding of this galaxy is now quite dark. Most of the matter has been depleted from this particular region of space and accreted into this structure, which we can see is starting to show the characteristic spiral arms of a disk-type galaxy. Let's just see that one more time, because it's quite nice to see it in action. Quite chaotic to start with, but as time goes by, more and more matter is flowing in from the filaments, and the spiral arms seem to sort of come and go because it's a rather chaotic process. But as more and more matter is brought in, that object in the middle, its gravitational pull, is pulling in more and more of these little knots, more and more of these what would be little satellite galaxies are being brought into the centre and merged into this galaxy. And as time goes by, you can see less and less matter is in the outside, more is being depleted from the outside, and more is collected on this spatial scale of order 50 kiloparsecs, roughly speaking the size of the Milky Way galaxy as it is at the moment. So TNG tells us how matter accretes into these regions where various filaments are meeting and producing these knots, where matter streams are colliding with each other and producing this accretion of matter. But we can ask the question, do the simulated galaxies that are generated by a simulation such as this, do they look the same as real galaxies? So here we see TNG 30. This is the cosmic web on the largest scales to give us an idea of what the cosmic web looks like. But if we home in and ask, well, what do individual galaxies look like in this simulation, we can ask, do these bear any resemblance to the sort of galaxies that we see in the sky? And if we compare them with a few observed galaxies which I've pulled off Hubble or other ground-based telescopes, here's a few galaxies, and I've chosen this one because it looks a little bit like this simulated galaxy. They appear to be two galaxies in collision, and indeed we do see that from time to time. We also see this faint area indicating that the galaxies are being distorted. And here we see two galaxies close together. Maybe they are trying to have spiral arms, but they are tugging on each other. The gravitational influence of the two galaxies is distorting those spiral arms. And yes, we do see that sort of thing in real galaxies when we look out into the cosmos. And here at the bottom we have a rather nondescript galaxy, but yes, we do indeed simulate those as well. This appears to be an elliptical type galaxy with no obvious spiral arms, and maybe it has a few little small satellite galaxies as well. Well, yes, we do see those in observations taken from ground-based and space-based telescopes. So we have some confidence that these sort of structures that are produced in the simulation do seem to have some sort of reality. But if we want to be really sure, we shouldn't be looking at the large-scale structure. We should be doing simulations on a smaller scale, not 300 megaparsecs, but perhaps 50 megaparsecs. So the higher resolution simulation TNG 50 hopefully will show more detail in the structures of these galaxies, which are a little bit difficult to see here because the spatial scale doesn't quite allow that. So let's look at some TNG 50 galaxies. So here's a selection. The simulation has been running for billions of years, and then the people who ran this simulation simply picked out a few galaxies that they could find and put them in this little chessboard here, just to show you the variations that you see in disk-type galaxies. We're not looking at those amorphous elliptical galaxies. We're looking at those galaxies which appear to have a disk-like structure. In other words, they look vaguely circular when we look at them face on and very thin when we look at them from the side. And on the left, the coloured pictures here show us where the matter is, where the hydrogen has started to collect. And of course, wherever we have hydrogen starting to collect, eventually we're going to be producing stars. And the pictures on the right, the grayscale images, are the same galaxies, but instead of highlighting them in colour to show where the hydrogen gas is, we're now showing where would we expect the stars to be shining. In other words, what do we expect the galaxies to look like if we were to look at them through a telescope? And I'm not going to go through them in detail, but I think if you can see those in reasonable detail there, I think you'll agree that some of these structures that we see are the sort of structures that we would expect if we were looking at a galaxy through a small telescope, or if we were imaging those galaxies with our CCD cameras. Those are the sorts of structures that we can quite believe that we're looking at, whether they be Messier objects or whether they be NGC galaxies. So again, by comparing dozens, if not hundreds, of simulated galaxies with actual galaxies we see in the sky, we can gain some confidence that the sort of galaxies that these simulations are producing do seem to be the right sorts of galaxies. We're not producing 99% garbage that we never see in the sky and only a tiny amount of representative. The galaxies produced do appear to be representative of the galaxies that we see in the cosmos. And in particular, it is possible to generate galaxies with masses of, let's say, about 200 billion stars. In other words, galaxies about the mass of the Milky Way, about the size of the Milky Way, and they seem to have the same sort of structure as the Milky Way. In other words, these disk-type galaxies with spiral arms, if we look in detail at what those galaxies look like face on at the top here and what they look like side on, remember the Milky Way galaxy is essentially flat with a little bit of a bulge in the middle. We can see that at the bottom here. There's the bulge in the middle of the Milky Way, as seen from the front, as seen from the side. And TNG50, the detailed simulation on the smallest spatial scales of the cube that the simulation is carried out in, that simulation appears to generate lots of galaxies, some of which look exactly like the Milky Way. They produce Milky Way analogues. So again, we seem to be producing the right sort of structures, and it's questionable, there's still work to be done. Are we producing the right number of spirals? Are we producing the right number of elliptical galaxies? Are we producing the right number of big galaxies? Are we producing the right number of smaller galaxies? Maybe there's a little bit of tweaking to be done, but that's why people are running the simulations, to try and understand what factors determine how big a galaxy can grow and how many satellites a galaxy might have, and why we have this difference between spiral galaxies and elliptical galaxies. So let's move on from accretion and think about what's going on in the heart of a galaxy. Supermassive black holes basically live at the centre of galaxies, and some are very active and some are not. So how do we know what lies at the centre of a galaxy? Well, we look at the stars, and the motion of the stars tell us what gravitating object is lurking at the centre of the Milky Way. If we see stars that appear to be moving in ellipses, held in place by some large massive object, but we can't see any object there, if it's invisible but very massive, then we know we've got a black hole. And if we record star positions, for instance in the Milky Way, we are of course relatively close to the centre of the Milky Way compared to the centre of many other galaxies. So if we record the motion of stars over many years, at least 10 years or so, we can see various stars in various orbits, and they all seem to be moving around an object that has a mass of approximately 4 million solar masses. That symbol, M circle dot, is shorthand for the mass of our Sun. Nothing special about the mass of our Sun, it's just a convenient unit. So all of these stars appear to be orbiting around an object which is at the centre there. It's very massive compared to a star, millions of solar masses, but it's also quite tiny, even taking into account the fact that the centre of the galaxy is many thousands of light years away. We still determine that this object must be quite small. If you look down here, this is our solar system to the same scale. That ellipse there is the orbit of Sedna, and the orbit of Pluto is one of those small circles which I'm pointing to with the cursor. So that object there, if it fits inside these orbits, it must be very compact. So this object has got a mass of 4 million solar masses and a size of no bigger than the orbit of Pluto. And there's a reminder that M circle dot is just my shorthand, well, universal shorthand for the mass of our Sun. Rather than work in units of kilograms, which would be silly, we talk about multiples of solar mass. So we've determined that we've got a 4 million solar mass black hole at the centre of our galaxy. We can't see it in normal images because there's so much dust obscuring our view. We have to use particular telescopes, usually infrared, to penetrate that dust to see what's going on. If we look in other galaxies, for instance, Centaurus A appears to be a very active galaxy. In other words, there seems to be a lot of energy coming out of that central region. We've determined that that particular galaxy has a supermassive black hole, which is much bigger than the one in the Milky Way. That one is 100 million solar masses, and it's responsible for these lobes that are being blasted out from the central engine of the black hole right at the centre of the galaxy. That black hole is producing enormous amounts of energy, which is producing most of the structure that we can see in that image. Coincidentally, 100 million solar masses, roughly speaking, that's the mass of the black hole in the centre of the Andromeda galaxy, just to give us a little bit of context. So by comparison, the black hole in the centre of the Milky Way galaxy is actually quite small. If we have a black hole which is only star-sized, then any star coming close to that black hole can be ripped apart by the tidal forces, and the matter doesn't go straight down into the black hole, just like water doesn't go straight down the plug hole. It tends to circle before falling into the black hole. And as it circles into this structure which we call an accretion disk, the matter gets very hot. And this accretion disk can radiate a great deal of energy. A substantial fraction of all the matter that is trying to fall into the black hole, a substantial part of that matter gets converted into energy, E equals mc squared, and then emitted as various electromagnetic radiation. And so when we talk about the radiation coming from black holes, we're not talking about what's inside the black hole coming out. We're talking about what's going on in the vicinity, just outside a black hole. That's where matter is getting very hot. That's where the energy is being radiated. In addition, we have these rather enigmatic jets. You see them coming out both directions here, perpendicular to the disk. These jets can take many different forms, but ultimately they are very fast-moving matter. And to be honest, we don't really understand the details of how those jets are produced. That's an ongoing area of research. It might well be that exactly how these black holes emit their energy can determine how galaxies form, but we're not quite there yet. We don't have all of the understanding of how these jets arise. So we understand that when matter is falling into a black hole, you could call that a black hole feeding on the surrounding matter, if you wish. We know that generates huge amounts of energy, but the detail of these jets is still a little bit of a mystery. If we look at Messier 87, M87, the galaxy itself is perhaps not that interesting. It's an elliptical galaxy. It seems to have no real structure whatsoever, certainly no spiral arms. But we do notice there's something very odd that seems to be coming out of the middle of the galaxy. If we use the Hubble Space Telescope to have a look in a little more detail, we see a jet coming out from the very centre of the galaxy. What's actually going on here, we believe, is that there's actually a jet coming out in both directions, just as I showed earlier, a jet going in one direction and a jet going in the opposite direction. One jet happens to be pointed towards us and one away from us. And the one that's pointed slightly towards us looks very bright, and the one that's directed away from us looks quite dim. So it looks a little bit unbalanced. We seem to have only one jet, but that's just, in a sense, an optical illusion. If we use a combination of radio telescopes, if we want to look in detail at what's going on in the black hole at the very centre, we need to have a fantastic resolution, which means a very large radio dish, or we need lots of radio dishes all working together, spread across the whole Earth, which then behaves like a radio dish whose diameter is the diameter of the Earth. This is the so-called Event Horizon Telescope, and that was used to image what's going on at the heart of M87. The black hole is called M87 star, as you can see in the bottom right-hand corner. Its mass has been determined to be about 6.5 billion solar masses, an absolute monster compared to the black hole at the centre of the Milky Way. So what we're looking at appears to be an accretion disk because matter is falling into this black hole. There's an accretion disk because all of the matter can't go into the black hole all at once, so a lot of matter is circulating, and parts of it look brighter than the rest because of the nature of how black holes work. There's a sort of shadow region in the middle of this donut, if you like, and that's because of the way the black hole is distorting space around it and is bending the light that is coming from the accretion disk to us. We think the accretion disk looks a bit like this. If you look at it from above, it just looks like a pancake. But if you look at the accretion disk from the side, it looks very odd because of the distortion of the black hole. So if we freeze that at that position, this accretion disk is pretty much like Saturn's rings in its geometry. It's very thin and it's quite wide. But this looks nothing like Saturn's rings simply because when we think of the accretion disk itself, we might think of it as simply a very flat disk, circular if seen face on and almost invisible if side on. But because of the very strong gravity of the supermassive black hole at the centre, light from the more distant part of the disk is being distorted by the black hole and arriving at us. In other words, we can see the other side of the disk. The one that should be behind the black hole appears to be visible. It appears here. It's almost like the back of the accretion disk has been flipped up, and that's the distortion produced by the black hole. Similarly, at the bottom, we see the underneath of the accretion disk on the other side of the black hole. Again, the light has been distorted by the extreme gravity of the black hole. So it looks rather odd, but we think that's what we're looking at when we see that image of the supermassive black hole imaged by the Event Horizon Telescope. We know these black holes can produce enormous amounts of power. Here is the galaxy Hercules A. It's an elliptical galaxy. Again, the galaxy itself looks very boring. There's no real structure there. We've no beautiful spiral arms or anything else. It appears to be just a big blob of an elliptical blob of stars all moving in various orbits rather than the sort of majestic spirals that we come to expect from the more aesthetically pleasing close-by galaxies. This Hercules A galaxy is quite large. There happens to be a little spiral galaxy just below it there. Nothing to do with Hercules A, but as it happens, that galaxy is about the size you would expect. If the Milky Way was placed at that distance, that's roughly how big the Milky Way would look. So that gives us an idea of scale. Hercules A is quite a bit bigger than the Milky Way if they were placed side by side. But that's not what's interesting about this galaxy. What's interesting about Hercules A is it has a supermassive black hole at its core, which is producing these enigmatic jets coming out. And we can't see them in visible light using the Hubble Space Telescope, but we can see them if we use the Very Large Array to look at the radio emissions from these jets. And then we realise that tiny, tiny supermassive black hole at the core is actually producing two jets which is blasting way outside the galaxy. You can see the scale, tens of times the diameter of the Milky Way, and these jets are slamming into the intergalactic medium. We tend to think of the space between galaxies as being empty. Surely there can't be much in between one galaxy and another galaxy. Well, there isn't much, but when you have a very energetic jet coming out from the centre of the galaxy, which is slamming into this medium, you get these shock waves, these spectacular shock waves, and the sheer size reminds you just how much power is pouring out of the supermassive black hole at its core. If a supermassive black hole is feeding voraciously, in other words, if a lot of matter, a lot of gas, a lot of stars are falling into that black hole, then we call that an active galactic nucleus, or an AGN. And the most energetic AGNs are called quasars. So a quasar is basically a galaxy that has a supermassive black hole at its core, and if enough material is falling in, then huge amounts of energy are radiated, and some of these quasars can be imaged even though they are billions and many billions of light years distant. When I told you about ancient light a little in the later part of last year, I showed that even with a camera and a telephoto lens, you can actually obtain an image of a quasar simply because it produces so much energy it's visible in a camera even at a distance of 25 billion light years. And again, that's just a sobering reminder of just how much energy is pouring out of these systems. Now we know that the supermassive black holes at the centre of galaxies are somehow related to the galaxies that they sit in. It appears that if you plot the mass of a black hole on the vertical axis versus, strictly speaking, not the galaxy mass, but the size of the bulge in the centre of a galaxy, we find that there's a sort of straight line relationship between the two. In other words, galaxies that don't have a particularly large bulge, like the Milky Way, has a lot of spiral arms but not a particularly large bulge in the middle, that has a relatively modest size supermassive black hole, only a few million times the mass of our Sun. But if we look in the top right at M87, that is a very large elliptical galaxy, and it has a monster-sized black hole at its core, 6 or so billion solar masses. So we know they're related, but the problem is, well, chicken and egg, which came first? We've seen how matter falling in through these filaments can start to produce galaxies, but we don't really know whether or not supermassive black holes start to form and then galaxies start to form around the supermassive black hole. Or does the galaxy start to form and then over time supermassive black holes start to agglomerate at the core of a galaxy? So more simulations are needed to try and tweak the at what point do we need supermassive black holes to be there in order to produce the sort of structures that we see in the universe around us. That again is ongoing research. So let's move on to the third element of the ABC. We've looked at the accretion, how galaxies form. We've looked at supermassive black holes, which are the engines at the centre of very active galaxies. Now let's consider how galaxies grow. They grow by colliding and merging with other galaxies, usually over time periods of billions of years. If we look at a picture, beautiful though it is, it can sometimes give the false impression that a galaxy is static. Well, yes, we know they're rotating, but if that galaxy takes 200 million years to rotate, you can imagine that's what it looks like now. And if we came back 200 million years later, it would have done one rotation, and we can quite easily believe that it would still look like that. So it's a bit deceptive, because what we have to appreciate is that over the lifetime of a typical galaxy, over billions of years, it can evolve and not simply sit there rotating. It can evolve and change through collisions and through mergers. We know that galaxies are interacting with each other. We see enough examples. Now that we have telescopes that can look a great distance into the void, we now see more and more and more galaxies that are interacting with each other. rather than just some of the larger galaxies which are quite close to us and appear to be islands that are separated from other galaxies. The deeper into space we look, the further back in time we look, the more we find lots of examples of galaxies interacting with each other. So on the right, we can assume that, well, those two galaxies, the large, what appears to be a very distorted spiral on the left, and another peculiar looking galaxy on the right, the head and the stem of the rose, if you like, they presumably are interacting with each other, but we can only fully appreciate what the nature of those interactions are through the use of simulations. We can allow simulations to allow galaxies to collide, either by forcing them to do so, or just by sitting back and letting gravity do its stuff, and then bringing galaxies towards each other. And then by looking at how they interact, we can get a better understanding of how galaxies change. And this is a rather nice simulation over a few billions of years on a spatial scale of quite a few galaxies. We can see that a galaxy's history is not quiet. It is absolute chaotic mess. Galaxies are colliding with each other, they're passing with each other, they're distorting each other. Some of these galaxies are spiral galaxies, some of the spirals are getting distorted by the fact that they're coming close to other galaxies. And what we've seen right in the middle of this particular video is a galaxy came in from the bottom, another galaxy came in from the top, and those two galaxies have merged. I'll rerun the video in just a moment. But before I do that, let's just note that something else we can learn from this still at the end of the video. Not only have we seen galaxies merge together and effectively grow by merging, we also notice that there are large numbers of small galaxies around. There's a very large galaxy in the middle here, but it's surrounded by a much larger number of tiny galaxies, satellite galaxies. And we can ask the question, is this reasonable? Can we expect a big galaxy to be surrounded by lots of small galaxies? Sometimes these simulations imply that every galaxy should have a large number of satellite galaxies. We look at the Milky Way. As of 10 years ago, we looked at the number of satellites of the Milky Way and we thought the Milky Way has about a dozen small satellites buzzing around us, the Magellanic Clouds and a few other dwarf galaxies. But now we realise we've missed quite a few satellites because our telescopes weren't sensitive enough, and now we have better technology. We realise that the Milky Way is not surrounded by a dozen or so satellite galaxies. It's actually surrounded by more like 100 satellite galaxies. In other words, it's actually a lot closer to what we see in this simulation, in which this large galaxy at the core appears to be surrounded by a very large number of smaller galaxies. So it looks like the simulations are getting it right. Observations were wrong, simulations were right. That's an interesting twist on the usual way it works. Also notice that despite the fact that we've had lots and lots of galaxies coming together here, there is still a fair bit of gas and light coming from the region in between galaxies. You can see that the gaps between galaxies is not black. There is definitely stuff there. There's hydrogen, probably a whole load of dark matter as well. But remember what we said about Hercules A? It was producing jets that were flying off into the void, but they were slamming into something, producing those huge radio lobes. That's what it's slamming into. This region of space in between the galaxies, the intergalactic space, is actually full of stuff. Not very dense, perhaps only a few atoms per cubic meter, but when you average over huge volumes, that's still a lot for those jets to go ploughing into. So let's look at this merger again. Watch out for a galaxy coming in from above, a galaxy coming in from below, and they will merge in the center of this image. So let's just rerun that video. Lots of turmoil, lots of spiral galaxies, and we see a large galaxy coming in from above, another one coming in from below. Getting closer, gravitationally pulling on each other. They just passed each other, do a little dance, and then they pass each other again, distort each other, and finally, after a couple of goes, they merge together as one huge galaxy. And during that time, other small galaxies are falling in. That galaxy is effectively a cannibal and is eating up other galaxies and some smaller galaxies. That is how galaxies grow. When we look, now we're looking at an observation, not a simulation. This is, I think, a Hubble picture, and we're looking at a galaxy cluster. And we note that when we look into the heart of galaxy clusters, we often find a larger fraction of the redder elliptical galaxies, the ones that don't have any particular spiral structure. They appear to be just elliptical blobs. If we look at what the star's doing, they're not all going round orbits in the same direction. They're going in random directions, compared to a spiral galaxy in which, in general, all the stars are going round the centre of the galaxy in the same direction. Basically, in the plane of the galaxy, all the stars are circling in the same direction. Most of the stars are circling in the same direction. But in these elliptical galaxies, the star orbits appear to be all over the place. But there's a lot of these elliptical galaxies when we look in crowded galaxy clusters. There's a lot more elliptical than spiral. And that's because more crowding means more collisions. And basically what is going on is that spiral galaxies which collide with other spiral galaxies effectively get so distorted, the spiral arms are effectively completely trashed, and the stars end up circling the centre of mass of the final object in almost random directions, and we end up turning spiral galaxies into elliptical galaxies. So you could argue that elliptical galaxies are simply the result of spiral galaxies colliding with each other. It's not quite as simple as that, but that's most of what you need to know in terms of the differences between spiral galaxies and elliptical galaxies. We know, for instance, that the Milky Way and the Andromeda Galaxy are going to collide. There's two spiral galaxies. We know the Milky Way is a barred spiral galaxy with 4 spiral arms, and the Andromeda Galaxy is very similar. Triangulum Galaxy M33 is close by, but is not going to take part in the collision which is going to occur because the Milky Way and the Andromeda Galaxy, being only 1 megaparsec, or 2 and a bit million light years, being relatively close to each other, they are gravitationally pulling on each other, and they are on a collision course. So here's a simulation of what that might look like. We take 2 beautiful spiral galaxies, we crash one into the other. The stars themselves are unlikely to hit other stars because the stars are so far apart. But the gas inside those galaxies is going to collide with the gas in the other galaxy. And you see that after one passage of one through the other, the spiral arms are disrupted, and then they pass through each other a second time, and eventually they merge together. And by the time they've merged together, the spiral arms are history. We now end up with something which will settle down into something like an elliptical galaxy. And we now can no longer tell whether a star originally came from the Milky Way galaxy or came from the Andromeda Galaxy. The collision of the two has wiped out that identity, if you like. So now we just have stars orbiting all over the place in this particular elliptical structure. And you notice that M33 is laughing there as it's escaped this particular fate. It's just a spectator in this particular collision. We can ask, what will it look like from our point of view? We can say, at the moment, we look into the Earth's sky and we see the band of the Milky Way, because of course we're inside the spiral structure of the Milky Way. So we're looking at the spiral arms from the inside, and we see the structure of the Milky Way. And on the left there, slightly off, we see the Andromeda Galaxy. This is, what have we got here? We've got Cygnus down the bottom with the North American Nebula stretching away, and then we have Andromeda on the left with the Andromeda Galaxy just here. And we can ask ourselves, what do we expect to see if we run the clock forward? What would it look like from our point of view? Well, the Andromeda Galaxy is going to start getting close. At that sort of distance, this is 1 billion years, the number's in the bottom right there, 1 giga year, 1 billion years into the future, the Andromeda Galaxy will be a little closer. and hence a lot easier to photograph for those interested in astrophotography. Milky Way looks pretty much the same. At that distance, the Andromeda Galaxy is not yet interfering with how stars are orbiting inside the Milky Way. At 3.7 gigayears, 3.7 billion years into the future, the Andromeda Galaxy is almost upon us. The outer parts of the Andromeda Galaxy are very close to the outer parts of the Milky Way, and they are starting to tug on each other. They're starting to tidally influence each other. But still, the Andromeda Galaxy is a spiral, still the Milky Way is a spiral. If you want to photograph the Andromeda Galaxy at this point, you no longer need a telephoto lens, you now need a wide-angle lens. If we go forward just a few 100 million years, all hell starts to break loose. The Andromeda Galaxy is now passing through the Milky Way. Remember, individual stars aren't colliding with other stars. Out of the 500 billion stars in the galaxy, maybe 1 or 2 stars might end up colliding with another star. But on the whole, the galaxies passing through each other will result in stars missing each other, but the clouds of hydrogen that are inside the galaxy will impact the other clouds in the other galaxy, and there will be a huge burst in star formation. Because the hydrogen clouds have been disruptive, you can start the gravitational collapse of clouds into stars. So these pink regions you see here are all the hydrogen regions that are starting to produce stars. If we go forward another 100 million years, it is even more chaotic. There is no way you can disentangle any star there that was in the Milky Way versus any star in the Andromeda Galaxy. And again, at this point, 3.9 billion years into the future, huge numbers of new stars are being made. So we should never think of galaxy collisions as being a bad thing. It's not a catastrophe. On the contrary, it's a way of actually promoting star birth. It actually increases the star formation rate considerably. Another 100 million years, the galaxies have now passed through each other for the first time and have left their distortion imprint on each other. So our view of our Milky Way is now very much distorted by the passage of Andromeda, and Andromeda now looks a bit of a mess. Its spiral structure has been disrupted. This is the 4 billion year point. They've passed through once. They will then slowly settle down, as we saw in that earlier simulation, until they form an elliptical galaxy. So this is 4 billion years. By 5 billion years, they will have passed through each other once or twice and then settled down. So perhaps you can just about see that there seems to be a brightish area in the top left and a brightish area in the bottom right. So those are probably the nuclei of the Andromeda Galaxy and the Milky Way that are now coming very close to each other. But notice that there is essentially no band of Milky Way. There is no spiral structure left in the arms of the Milky Way. Perhaps we shouldn't call it the Milky Way, because now the Milky Way and the Andromeda Galaxy are one. We cannot tell them apart. We can't draw a dividing line between the two. So we need to come up with a new name. Milkdromeda, some people have suggested. Andrilke? No. Androway? I don't know. Pick a name. We need a new name. We've got 5 billion years to sort it out, but we do need a new name for this new galaxy. Eventually, we assume that the nucleus of Andromeda and the nucleus of Milky Way will come together. Remember, there are 2 huge black holes. There are 2 supermassive black holes now physically quite close to each other, and they will attract each other, and presumably they will merge. The black hole that was at the centre of the Andromeda Galaxy is much bigger than the Milky Way's black hole, so presumably the Andromeda black hole will swallow the Milky Way black hole. And then huge amounts of matter will be falling into this newly made black hole. So you could speculate that once the Milky Way and the Andromeda collide, is it going to turn our new galaxy, Milkdromeda, is it going to turn it into a quasar? Because the new black hole Unlike the two black holes we've got at the moment, which are not feeding on anything, no substantial amount of matter is falling into either black hole. But when they merge, it is quite possible that huge amounts of matter will be falling into the new black hole, and it might turn our galaxy into a quasar. And that will be bad news if we are around and too close to that nucleus. We won't, of course, necessarily be at the same distance we are now, because all bets are off when two galaxies collide. So we will have to worry about that in 5 billion years' time. But look on the bright side. At least lockdown will be over by then. So we'll have that less to worry about. So I've been telling you about the three principal factors that influence galaxy evolution. Galaxies are formed by a process of accretion, matter falling from the original matter produced in the Big Bang, collapsing under accretion, forming these filaments and voids, and matter streaming down the filaments and accreting purely under the influence of gravity, with a little bit of influence of what stars are doing to stop that inflow of matter. We know that galaxies have black holes at their core. Some are very active, some are very quiet. We haven't quite got the evolution of when black holes formed, and did they then produce galaxies around them, or did galaxies start to form and then start to produce black holes? But we now have a better understanding through simulation of exactly how collisions of galaxies that make galaxies grow, make galaxies merge. We now have a better understanding of how we can end up with large elliptical galaxies, starting with a larger number of smaller spiral galaxies. So next time you look at a galaxy, whether it be through a telescope or whether you're just admiring Hubble pictures, remember the ABC. If you remember the ABC, then you can remember essentially why galaxies form and how they grow. Thank you all for listening.